interestingly, this intuitive idea that we obtain using geometry has a very elegant algebraic form. So let's consider this. So I have the same number line. Instead of using colors, I have used some different symbols. These are some crosses, these are some circles, and these are some triangles. Now I want to capture the idea algebraically that these things are separate clusters. So for that, what I will do is, I will say how much do these points vary, and that I can capture using this idea. Suppose these three groups have their respective centers, and I will express the numbers as yij's. So I is the variety and j is the jth plot under the variety. So it is the jth plot under the variety. So in this case, I is 1, 2, 3 and j runs from 1 to ni. They may differ for different i's. Now when I have this situation, then if I want to say how tightly these things are clustered, I can measure it in this way. For each one, I find out its average. So suppose this happens to be, say, cluster 1, this is, say, 2, and this is, say, 3, I1, 2, 3. In that case, the center, I am going to call it y3 dot bar. The dot means that I am averaged over j. So this will be y1 dot bar and y2 dot bar. So to measure how tightly clustered these are, I will do the following. I will take y3j's, all the points here, find out their difference from their center, and then I will square and add. So it is basically computing the variance of this group alone. Similarly, I can do it for this group, do it for this group, except that I am not dividing by the total number of observations, n3 minus 1 or n3. Now what I will do is, I will take the total of all these things. So basically I am trying to do average of the variances, except that I am working with only the sum of square parts. So if I add over I, so I will make this I, that will give me an idea how tight the clusters are. I am working under the homoscedasticity assumption. So early statisticians always use that assumption. They did not even know that heteroscedasticity would cause a problem. So they were thinking about the simplest possible case. So we have this thing, and they are trying to measure this tightness of the clusters by this number. Loosely speaking, I have not divided by 3 and all those things. And they call this quantity the within sum of squares. So WSS, because it is within. Now we want to know how well separated these three averages themselves are. So as if you have one point at this average, another here, another here. In that case, you can do the same thing, but now with the cluster means, and that will be yi dot bar minus y dot dot bar. Y dot dot bar means I have averaged over I and I have averaged over j. That is, this is the master average. And again you compute the variance like thing. So you do by I, but now I will multiply this with ni. This is the idea that as if all these points are nothing but y3 dot bar. So there are n3 many points which are equal to y3 dot bar, n1 many points which is equal to y1 dot bar, and so on. That is why I am multiplying this with this factor. So this is the weighted average of all these, and the weights are being these ni's. These things they call between sum of squares. So between means between the clusters, and these are within the clusters. And quite interestingly, something that impressed early statisticians very much, you have a nice algebraic identity which goes like this. If I add ij, yij minus y dot bar square, this surprisingly breaks up between these two things, BSS and WSS. The proof is very simple. You just introduce this yij minus yi bar plus yi dot bar minus this. You just expand it in this way by subtracting and adding this quantity, then consider this as A, this as B, and apply A plus B whole square formula. The cross term will just cancel off and you will be left with BSS plus WSS.